Good afternoon, everybody. Thank you, Maria, for your kind introduction. Um, I would like to present today, also on behalf of my co-authors, a work that we performed on the accelerated carbonation of ordinary Portland cement paste and its effects on microstructure and transfer properties. I would like to start by introducing the topic a little bit and the motivation of why we did this work. I think there is no need to go into details regarding carbonation mechanisms because probably everybody who is attending this presentation is more than familiar with. I just wanted to point out that carbonation mechanisms are present in cementitious materials, um, providing effects that are not only negative, such as the river corrosion or increase in porosity of carbonation-induced shrinkage cracking, but also positive effects such as self-healing of cracks to carbonation and carbonation curing, which actually improve the mechanical properties of the material, but also decreases the permeability of the material and therefore increases its durability. Um, no matter which is the effect that we are looking at, the mechanism is likely to occur on unsaturated concrete, which is unfortunately the exposure conditions that most of our infrastructures are subjected to, and therefore the transfer properties of the material are of paramount importance if one wants to understand the kinetics of the mechanism and to predict what's the durability of the structure, for example. That's why in this work we have, we propose a comprehensive methodology to study the evolution of microstructure, hydrate assemblage, and transfer properties during carbonation. So this methodology can be later used to provide input or validation to models that can help predict carbonation um, kinetics on real structures. I would like to talk a little bit about the methodology that we used. We perform all the experiments in a cement paste with a water cement ratio of 0.6. First, we cast the samples and cure them for around 90 days um, in sealed conditions. Then we precondition the samples at a temperature of 20 degrees and a relative humidity of 65%, which we would later use as well, same conditions for the accelerated carbonation conditioning. And after this preconditioning phase, we assess the initial properties of the material using the methods that I list at the end: a dual microcomputed tomography, phenolphthalein method, thermogravimetric analysis, and dynamic vapor sorption. After this initial assessment, we expose the sample to accelerated carbonation with a CO2 concentration of 5%. And we reassess the properties that I would talk a little bit more later using the methods that I list here during and at the end of the experiments as well. So I don't need to go into detail regarding the thermogravimetric analysis methodology. I just wanted to mention that we use it to quantify the degree of hydration of the material prior to the carbonation exposure and to quantify the contents of portlandite and calcium carbonate before, during, and after carbonation. Dynamic vapor sorption we use to obtain sorption and desorption isotherms. The method, basically like exposes the sample to different relative humidities, and the equilibrium mass of the sample is recorded. And this is possible due to the presence in this instrument of a very precise and sensitive microbalance. With this sorption and desorption isotherms, provided that we use only one constant temperature, we could obtain the water retention curves, which is usually used to model moisture transport or any transport process in cementitious materials, and the relative permeability function, which is a reducing factor of the permeability as a function of the saturation of the material. But not only DVS can be used to find other properties as well. And we use as well dual X-ray microcomputed tomography in two different types of samples. In microbeams, which we call like that because the section was of 380 by 380 micrometers, and that we use to extract the pore structure employing the dual X-ray CT methodology, and a macrobeam that we use as well to map the porosity in 3D of the sample during carbonation, to use it as a way to quantify the penetration, the position of the carbonation front during the experiments. How do we do this? First, we acquire the 2D radiographs of the same sample two times. One when the sample is completely dry, and the other one after vacuum saturation. Of course, for each of these sets of 2D radiographs, we perform a volume reconstruction to transform from 2D radiographs to a 3D volume. And we correct for different image artifacts that can occur. And we perform as well filtering in order to prevent the propagation of image noise. After we have the volumes and we have the different slices for the two states, dry and saturated, we perform a 3D registration. This is kind of a volume image correlation method in which we align the stacks. So for each point in the material, we have a perfect correspondence of the two scans. And then with these two sets per sample, we perform data analysis, namely the porosity assessment, that we have a distribution in 3D, and we can simulate permeability and tortuosity on the obtained pore structures. I just wanted to show you here the settings of the scans. So basically, I just wanted to show you the different resolutions that we could obtain with the different samples. For the macro beam, we had 7 micrometers of resolution, whereas for the micro beam, we had 0.63 micrometers. And this is the operation that we perform with the two stacks in order to obtain a map of the porosity per voxel in the 3D volume, because we could make a correlation, because we use attenuation as a method to obtain the gray values in this methodology. We can perform this operation that I present in the slide to obtain the porosity of each voxel. With the pore structure that we obtain, as you can see in the render in the slide, we could perform tortuosity simulations using an open source code that was already available from Prometilla et al. And we also perform lattice Boltzmann simulations to obtain the intrinsic permeability of the input pore structure. So I would like to share the results. So from the TGA analysis, we could quantify the portlandite and carbonate content, and you can see that already after 15 days, the both carbonates and portlandite were in equilibrium in the first 3 millimeters of from the exposed surface, whereas already for 22 days, also the region between 3 and 6 millimeters was almost in equilibrium as well. But of course, this is a very coarse method to find the carbonation depth. So that's why we use the macro beams, from which we determine the 3D distribution of the porosity, and then use the porosity profiles to determine the carbonation depth. And then when we compare to the profiles obtained with the phenolphthalein method, you can see they are very similar. We obtain as well the porosity, um, and we compare to the porosity obtained from other methods. So you can see from the dual microcomputed tomography, as well as from the DBS and the gravimetry, the values are very similar before and so for before the carbonation, and then also for the after the carbonation. So you can see the porosity decreased upon carbonation. And from DBS, we could also extract the differentiate between gel porosity and capillary porosity, as you can see, according to this method. Upon carbonation, the cement paste capillary porosity almost didn't change, whereas the gel porosity reduced, got reduced drastically. From the simulations performed on the pore structures, we obtain values of tortuosity and permeability. As you can see, although the values are way different from absolute values that can be found in literature, they do follow the trends that are expected upon carbonation of Portland cement paste, namely the tortuosity is increased because of the precipitation of carbonates in the pore structure. The path gets elongated, and the permeability decreases, not only because of the tortuosity increase, but also because of the porosity decrease. And last, we obtain the coefficients of the water retention curve and the relative permeability functions that can be readily used for simulating transport in cementitious materials. And to finalize, I would like to remind you of the main takeaway points. So we could successfully use dual micro CT to assess the carbonation depth from porosity profiles. And we can also say that the porosity obtained from dual CT scans presents very similar values to other methods that are currently used in our field, like DBS and gravimetry. That although the tortuosity and intrinsic permeability simulated from the highly resolved CT scans are under and overestimated respectively, the change in their magnitude due to carbonation follows the same trends observed in experiments in literature, and can be used for qualitative assessment. We also readily obtain the Moellem and Van Genoegten parameters and their evolution throughout carbonation. And regarding the material that we use in this study, the cement paste, the Portland cement paste with water cement ratio of 0.6, carbonated very rapidly in optimal relative humidity of 65% and a concentration of CO2 of 5%, with a final carbonation depth after 22 days of 7.5 millimeters. Thank you very much for your attention, and I am more than happy to answer your questions.